In previous videos on this channel, we looked at this Xerxes PCB, which is an AMD Xilinx Spartan 7 FPGA-based hardware with some external memory, debug interfaces, various power regulators, as well as this audio front end. In essence, this PCB is used for this channel to demonstrate various aspects with regard to PCB design, but also audio DSP, digital signal processing, on an FPGA. Building up to all of this, we're going through all these various aspects of this PCB. This first version of this PCB was manufactured and assembled by PCBWay in China, more about them in just a second. But this PCB had on the bottom left here, in the middle left here, this ISSI HyperRAM, which is effectively an Octo SPI interface RAM interfacing with this Spartan 7 FPGA. Now as an update, I found interfacing with this HyperRAM a bit tedious. Therefore, for a revision B of this PCB, instead I added in this DDR2 memory, which hooks up to the Xilinx Spartan 7 FPGA. And this is pretty much the only change to this revision B. This DDR2 memory and interfacing it with the Spartan 7 FPGA is the topic of this video. How do you do the pin-out and how do you do the PCB design? In a future video, we will then be talking about implementation, so actually incorporating this DDR2 memory in FPGA designs, be this with a soft-core microprocessor or something else. But this video will focus more on the hardware electrical side of things. The reason I went with the DDR2 interface is simply for simplicity. It's very easy to hook up to the Spartan 7. As we'll see, the AMD Xilinx tools pretty much natively support DDR memory. And I chose DDR2 because it's comparatively low speed, we don't have to pay too much attention to the PCB design, and I can reuse this 1.8 volt regulator I already have on the board. DDR2 memory runs off nominally 1.8 volts. If I'd gone with DDR3, I would have had to add another regulator in, a 1.5 volt regulator, which I didn't want to do. All I wanted to do was change out the memory. So that's why we're talking about DDR2, even though it's a bit of an older standard these days. If you're interested in the previous tutorials, make sure to check out video number 109 on my channel, which is a basic FPGA design tutorial for custom hardware, so setting up the toolchain, writing some Verilog, doing some simulations and implementations. This will also give you a good overview of the Xerxes PCB and hardware and what's on it. I also have a video number 108 on my channel, where we configure a soft-core microcontroller on an FPGA and write some basic programs for this. Thank you very much to Altium for sponsoring this video. I designed these Xerxes PCBs using Altium Designer, and I'll show you some tips and tricks in this video as well. If you'd like to give Altium Designer a try for yourself, make sure to check out the link in the description below, or go to altium.com/yt/philslab, and you can get yourself an Altium Designer free trial, as well as 25% off your first license purchase. This will also let you check out all of the cool new Altium 365 features. A huge thank you also to PCBWay for sponsoring this video and making these real-life hardware designs possible. The Xerxes Rev A PCB was manufactured and assembled by PCBWay in China. This is a 6-layer PCB, as we'll see in just a second when we go through the hardware. And I've had many other advanced PCBs manufactured and assembled by them, and they've always turned out great, such as this AMD Xilinx RTX 7-based PCI Express hardware accelerator, or this AMD Xilinx Zinc system-on-chip hardware design featuring gigabit Ethernet, a gigabyte of DDR3 memory, and various other interfaces and peripherals. I'd strongly suggest checking them out. I use their advanced PCB service. There are many options you can choose, up to 60 layers, which is rather impressive. Loads of different material choices, HDI PCBs, so featuring blind and buried vias, very narrow track spacing and feature sizes, and many different options you can choose from. I'll leave a link to them in the description below. Here we are in Altium Designer, looking at Rev B of this Xerxes PCB. In the center, on the right-hand side, we have the AMD Xilinx Spartan 7 FPGA. Being an FPGA, it's highly configurable. So surrounding this, we have some QSPI flash memory, we have a debug interface, an audio codec, and various other peripherals, for example, potentiometers, which are hooked up to the FPGA's ADCs. The FPGA itself doesn't have very much volatile memory internally. Therefore, we have to provide some external and volatile memory. In this case, I went with a DDR2 memory module, which is this block on the left-hand side. You might be asking, why did I choose DDR2? And as I said at the beginning, this is because I didn't want to add any more power regulators in this design. On the left-hand side, you can see the voltage regulators, 1 volt, 1.8 volts, and 3.3 volts. All these sections are required by the FPGA itself for its core voltages, as well as the bank voltages, which interface with the QSPI flash memory and various other peripherals. Had I chosen, for example, DDR3 memory, I would have had to add in another regulator, which gives us 1.5 volts. which means I would have had to shift around all of these regulators, add in more space, and it would have been quite a big of mess. All I wanted to do was replace the HyperRAM with a DDR memory alternative. Therefore, I went with DDR2 memory. DDR2 memory runs normally off 1.8 volts, and surprise, surprise, I can use the 1.8 volt regulator to supply that. Of course, you have to take into consideration power and current consumption as well. DDR2, of course, is slower than DDR3 on average, but for this design, this was completely fine. I don't have particularly high bandwidth requirements, and DDR2 for this audio processing system is sufficient. What we need to do as designers, and what can oftentimes be rather daunting, is deciding on a pinout between FPGA and our DDR2 memory module. And this, of course, is similar for DDR3 and DDR4 and so on. Given that FPGAs are so flexible, if I switch to 2D view, our FPGA is this BGA package here, and we have loads of these free pins, which I maybe could have used to interface with our DDR memory module on the left-hand side. However, I came up with this pinout. As you can see here, there are these various data byte lanes and address command and control signals, which we'll see later. Why did I choose these? And why did I choose this particular memory module? How do we do the power and decoupling? And I'd like to address these, at least the basics, in this video, as this can be rather overwhelming. The first thing I'd like to show you is the Vivado tools, which are part of the AMD Xilinx family, which guide us in doing the pin-out, as well as choosing our part, which can interface with this AMD Xilinx Spartan 7. If you'd like to follow along, I'll leave a link to this in the description below, but I'd strongly suggest downloading AMD Xilinx Vivado, which is free for most AMD Xilinx FPGAs and system on chips. This is my preferred design tool, which lets me verify the designs before generating the hardware. I've got Vivado open now, and we'll just create a demo project for us to decide our memory module and then figure out our pin out. I'm just going to leave all of this blank. Whilst your project is fine, just click next, and we need to choose our part. And this depends on what part you're using. Of course, for parts other than AMD Xilinx, such as Lattice or Altera Intel, this will be different. But I prefer Xilinx parts, so I go with this. My part is an XC7S25 and a CSGA225 package, and my speed grade is 2. So this is the device I'll select. And click next and finish. Keep in mind, we just want to find a pinout for our DDR and choose a suitable and appropriate DDR2 memory module. If you want to do this for DDR3, it's a very similar process. Left-hand side, I go to IP Integrator, click Create Block Design, and nicely enough in these Vivado tools, as free IP, if we go to the Add IP button, this little plus at the top, we can type in MIG, which stands for Memory Interface Generator. Double-click on that. This is the tool we'll also use in future videos to then create our DDR2 memory controller as a soft controller within the FPGA. And it's really nice that this is packaged essentially for free. We can double-click on this, and we'll just customize the basics, and we'll use this tool to find suitable DDR2 modules. I'll just click Next. I'll set this to Create Design. And we'd like to choose DDR2 SDRAM. And immediately we can see what types of memory are compatible with this particular FPGA. So that's a really nice hint. Here we go. What we're now interested in, and why I'm showing you this, is because of this memory part section over here. On the right-hand side in this drop-down, we can see they have already predefined memory modules that are compatible with our FPGA. These happen to be all Micron parts. As you can see by the first character as MT, this will be Micron parts. These will come in different data widths, so 8 bits, 16 bits, and also densities. So you can get a gigabit of memory, 512 megabits, and so on. This is a really good starting point to figure out compatible memories. Also later on in a future video, we'll see we'll have to enter timing parameters for our DDR memory. So this is a really good starting point to see what devices we can work with. Of course, you can go with datasheets and datasheet specifications such as timings, maximum speed grade, and so on. But for simplicity, I really like using this tool. If you look at these memory names here, for example, MT47864M16-25, and then we move over to the schematic, the particular memory part I chose was this Micron memory module down here. This happened to be the memory module I chose for several reasons. First of all, it was available in the AMD Xilinx tools in Vivado, meaning I knew it was natively supported. I might have to tweak some of the timing parameters depending on part variations, but it's DDR2 memory. It's abundantly available at the time I was designing the hardware. It's rather cheap in low quantities. It's about €4 per module. It's got a 16-bit wide data interface, and it's a 1 gigabit of memory, maximum clock frequency of 400 megahertz, and again, compatible with this AMD Xilinx FPGA that I'm using. So this is the part that I chose. In any case, this is why I think it's really important that you use vendor tools, you look at the datasheets and application notes to make informed decisions on what memory parts are compatible. You definitely want to do this before designing your PCB, designing your hardware, is to make sure you have compatible memories in place. We'll come back to this in just a second, also to do our pin-out. In any case, that's why I dropped down this MT47 DDR2 module on my schematic. The schematic symbol has two parts. One, of course, is the power section, and one is the I/O, the signaling. I won't be going into too much detail on DDR signaling, but in general, we have several signal groups. And I've color-coded these in Altium Designer. First, on the left-hand side, these blue signals are the address command and control signals. These act as one group and also have to be delay matched, which we'll see later on as one group, and routed as one group. On the right-hand side, we have the individual data byte lanes. Because this memory, as we saw, is a 16-bit wide bus, we have 2 byte lanes. So 8 bits per byte lane. We have DQ0 to DQ7 and DQ8 to DQ15. Every byte lane has a corresponding data strobe. This is a differential pair, such as this DQS0 belongs to the first byte lane, and DQS1, this differential pair, belongs to the second byte lane. Corresponding to every byte lane, we also have a data mask. So DM0 corresponds to DQ0 to 7, and data mask 1 corresponds to DQ8 to DQ15. So 2 different byte lanes. All of these I/O signals have to be routed and connected to our FPGA somehow. We'll see more of this and also the termination and pull-down resistors later on after we've done the pin-out. Powering a DDR2 memory module is fairly straightforward. Again, we need a 1.8 volt nominal supply voltage. We have VDD and we have VDDQ. VDD effectively you can think of as the core voltage, and VDDQ is the driver voltage. The address command and control signals are effectively inputs only. So they are being controlled by the memory controller, in our case the FPGA, but the data signals are effectively bidirectional because you want to transfer data into the memory and out of the memory. Therefore, the drivers also, of course, need to be powered. We also have a reference voltage, and that can be generated by a dedicated supply, but for something as simple as this, we can just use a resistor divider, so equal valued, low valued resistor, some filtering capacitor to generate a reference of half the supply voltage. And then, of course, we have all of these ground pins. In terms of decoupling, if nothing else is stated in an application note or datasheet, per VDD pair, so per 2 pins, I'd recommend adding in one small decoupling capacitor, such as 100 nanofarads, 0402 or 0201. Per approximately 10 VDD pins, I typically also add in a bulk bypass capacitor, for example, this 4.7 microfarad capacitor. Now that we have the pin-out, and now that we've chosen a seemingly suitable memory module, we need to connect this up to our FPGA. Before we can address the pin-out of the FPGA and how that'll interface with the DDR2 memory, we need to know about FPGA Banks. To do so, let's look at the power section that powers this AMD Xilinx Spartan 7 FPGA. Contrary to most microcontrollers, powering an FPGA is rather more involved. We have a lot of ground pins and a lot of power pins, but importantly, we have power pins that have different requirements, oftentimes very many different voltages. This Spartan 7 FPGA is comparatively quite simple. We only need about 3 supply voltages. For example, the internal voltage at 1.0 volts, auxiliary voltages at 1.8, and bank voltages depending on your design, but I've used 3.3 and 1.8. Bank voltages. Banks are effectively groups in an FPGA typically used for I/O. With this particular Spartan 7 FPGA, we have bank 14, 15, and 34 as our main I/O banks. These can be powered by separate voltages, so I could have a different voltage for 14, 15, and 34. The actual I/O for the banks is shown here, so bank 14 has all of these pins, which are very, very flexible. We have bank 15, which connects to other peripherals, also very flexible, and bank 34, which you'll see right now, is actually our DDR2 bank, and I'll show you why in just a second. In any case, as I said before, these banks can run off different voltages, which we're also doing here. Some banks will have constraints. For example, the non-volatile memory, this QSBI flash which configures the FPGA, has to be in this particular bank, so bank 14. Certain clocks have to be attached to certain clocking capable pins, and there are constraints depending on your design. I happen to have done the pin-out predominantly based on PCB routing and layout to make my life easy, and some certain constraints, for example, this QSBI flash memory. This meant that bank 14 and 15 are being used, for example, for ADCs, peripherals, codec interfaces, and so on, and these are both running at 3.3 volts. Them both running at 3.3 volts means we can't attach the DDR2 memory. DDR2 memory runs off an I/O standard of nominally 1.8 volts. Therefore, the only free bank in this 3-bank FPGA was bank 34. Bank 34 was completely free, and therefore I designated this to be my DDR2 memory bank interface. Therefore, looking at the power section, you can see bank VCC034 is hooked up to 1.8 volts, which is our DDR2 I/O voltage for exactly this reason. Especially since we're only using a single memory module with only a 16-bit wide data bus, this means this could actually fit into a single bank. If you're using multiple memory modules or wider data bus widths, you typically will need to spread your DDR interface across multiple banks. But for this very simple interface, I could fit everything into one bank, which makes my life a lot easier. It also makes timing a lot easier as well if you don't split across many banks. So I'd suggest if you don't have particularly stringent requirements, pop it all in one bank. And that's exactly what I did. So all of the address command and control signals, all of the byte lanes, as well as my clock source, particular for the DDR memory, feeding the DDR memory controller, is hooked up to this bank. The question is, this doesn't seem particularly ordered. It's A6, A2, the row address strobe, column address strobe, and so on. Why is this ordering like this? Why is the pinout like this? We have so many different signals, how do you even come up with this? So this seems quite hard to do. The good thing is, it's actually fairly straightforward with the vendor and manufacturer tools. The first important thing is that I wanted to keep everything in this single bank. The single bank powered off 1.8 volts, and this is the only bank that interfaces with the DDR2 memory. The second constraint is, moving over to the PCB design, is that I wanted to make my PCB design as simple as possible, meaning minimum via transitions, short distances, and no crossings if I can avoid them. I actually worked out the pin mapping pretty much purely based on the PCB design. Very simply speaking, I have my FPGA in the center, everything around it was fixed, and I knew my memory should be somewhere on the left-hand side, and nicely enough, this was close to all of my bank 34 I/O pins on the FPGA. So on the left-hand side is where all of my FPGA bank 34 pins are, so naturally it makes sense to put my DDR2 memory module there as well. I want to keep it close to make sure my traces are short, but then to get to the pinout, all I do is, after placing my power and ground pins and my vias, is simply root out and see how feasible some connections were. If I just try to fan out this BGA package, how easily can I do that without any crossings and so on? I do this for the address command and control signals, but also for my data signals. Keep in mind, the FPGA is very, very flexible, so this is definitely how I would start. I would just see what's easiest to route and lay out first. So I just do point-to-point connections. I would assign pads on the fly, just making sure I can route this out as easily as possible. Afterwards, I would then verify that pinout with the vendor tools. So that's my suggestion. Place the parts appropriately close to the banks where they have to be, align them, and then route over and get your initial pinout just by doing the PCB layout and routing. Once you've done that, you can transfer a preliminary pinout of the FPGA to your schematic, noting down very simply the net names, what connections you've made. Keep in mind, you don't want to spend very much time on this. You want to do this quickly because you might have to change your layout and routing depending on the constraints of the tool. But this is what I did first. Then I went back to Vivado, the memory interface generator tool. I changed my data width to 16, of course, then just flicked through until I get to the pin bank selection mode. Here you can either choose new design, where the tool will pick the optimum banks for the design, and this might be a good starting place, or you can go to fixed pin out to verify your pinout. And that's exactly what I did. Here you have all of the DDR signals listed, which we saw previously, and now we can choose what bank they should be in, and then of course what pin number. So everything, of course, will have to be in bank 34, so you could select that, and then you can choose whatever pin you routed to in your preliminary fan out. You can save this data in a UCF file, and that's exactly what I did, and I'll just read that in. Now with my pin out file loaded in, you can see every signal is mapped to a specific pin number. Then you can click on validate, and the tool will tell you whether your pinout is valid or not, and if it isn't, it'll tell you reasons why. And this is exactly how I generated and came up with the pinout. What you will notice is that, for example, DQ0 to DQ7, my first byte lane or byte group, has the same byte number, this T2. My second byte lane, so DQ8 to DQ15, has a different byte number, so T3. We can see this in the schematic here. On the pin naming of my FPGA, we have these certain byte numbers, so T2, T3, T1, and T0 in this particular bank, and I strongly suggest, while you're doing the initial pinout, to keep the byte lanes within byte numbers. What you'll also have to do is keep your strobes, so DQS, mapped to the relevant strobes and strobe-capable pins on your FPGA. So pin J4 and J3 is strobe-capable DQS and DQS, also with a positive and negative part of the differential pair. So there are some rules you have to adhere by, but these are the very, very basics, and your tool will tell you if this is working or not. And this is exactly how I got my pin-out. So again, starting very quickly, placing my parts, placing my vias and my power delivery first, to making sure I can route past all of these vias and wider traces. And just to get an initial pin-out, I route very quickly left to right, making sure I have minimum crossings. Once I verified the pin-out, I could then complete this routing. And that's how quickly, at least for these AMD Xilinx parts, you can get a pin-out. What we also have to consider, however, is that in these banks, we also have these VREF pins. So VREF on D1, for example, or VREF on M3. Because this VREF, for example, down here is actually mapped to DQ14, we can't use an external VREF. Now this in turn means practically for us that we have to use an internal VREF for the FPGA side. We can't maybe run our external memory as quickly as we want it to. Therefore, it might make sense to spread the DDR signals across multiple banks so we can have external VREF attached. But for this very simple low-speed design, having an internal VREF is completely fine. But there are some things to watch out for, of course. Additionally, I left this pin H4 free, the wire I attached a 100 MHz CMOS oscillator to this multiple region clocking capable pin, MRCC for short, and this will actually then be the primary clock source from the memory interface generator, this MIG, which generates the DDR2 memory controller. This I thought was important as well, to have my clocking source directly in bank 34. But that's how very simply we can generate the pin out for an FPGA, specifically AMD Xilinx parts. What I then like to do is, of course, color code, because this is important for layout and routing, as well as designate any differential pairs, add some blankets and parameter sets, for example, telling my ECAD tool, Altium Designer, the net class name, because we'll have to match the delays to a specific tolerance, let's say 150 picoseconds in this example. So color coding, adding rules, and giving designated net classes and net names, I think is very, very important. You will have also noticed the termination resistors or lack of termination resistors. The data signals or the data I/O are internally terminated for DDR2, so we don't have to add any external termination resistors here. Now the address command and control signals theoretically should have termination resistors, and there's various termination schemes which we'll discuss in a future video. For something as fairly low speed as this, I've decided to not include termination resistors. I've only included a termination resistor on my differential clock pair for the address command and control signals, which is this 100 ohm resistor. 100 ohms because all of my DDR signals are routed as 50 ohms single-ended and 100 ohms differential, and that's why R250, this termination resistor, is at 100 ohms. Other than that, it's suggested to have pull-down resistors, so not termination resistors, but pull-down resistors of about 4.7 kilo ohms on the clock enable, as well as the on-die termination, and optionally also on the chip select signal as well. This can actually be omitted in this case. But keep in mind, termination depends on your PCB layout and routing structure, your data rates, rise and fall times. There's many things you need to take into account. But for fairly old, fairly slow systems such as DDR2, this is the bare minimum I would suggest doing. When it comes to PCB layout and routing, because we've done quite a lot of the steps beforehand when we're figuring out the pin out, where to place our memory module, and so on, we've already seen quite a lot of the things we have to do. DDR2 layout and routing is actually not too critical. It's a fairly old technology. Just some key points. I would suggest placing your DDR memory module close to your controller, in this case the FPGA, the reason being you want to keep your trace length as short as you can. In terms of BGA decoupling and fan out, I've placed all my vias and power circuitry first, so every power and ground pin, I have one via with a very wide trace directly into an internal ground or power plane. On the bottom side, I can then place my decoupling capacitors, where I have my power and ground vias close together, and with short wide traces to my decoupling capacitors. The signal I/Os themselves can then route past these vias because we've placed them first, and I've routed these traces as 50 ohm single-ended or 100 ohm differential. Trying to keep at least somewhat sufficient spacing between the traces. I don't want to have them grouped very, very tightly, for example like so, just giving them some space to breathe. It's okay as they are routed relatively short. The color coding is nice because I can see at the top I have my address command and control signals, then I have these two different byte lanes, and they're routed in their own groups. Point-to-point connections between memory and controller, or FPGA. If we go to the net classes, we can see, because we've added them in the schematic, if I click on address command and control and sort by delay, Altium Designer nicely enough shows the total delay, and this is including package delays of my FPGA. So if I click on individual pins, you can see I've added in the package delay of the pin itself, which I got through the tools as well. You can see my maximum delay is about 213 picoseconds, and the smallest delay is about 90 picoseconds, which means they're matched within about 120, or definitely less than 150 picoseconds. And at the bandwidths and speeds you're running at for this DDR2 memory, that is completely fine. Same thing goes for the byte lanes. They're all matched with 150 picoseconds, so byte lane 0 within itself, and byte lane 1 within itself. Keep in mind, these are 3 separate groups. They don't actually need to be matched between each other. For some signals, I did have to go through vias. I probably could have adjusted some things and not needed vias, but for the way I already had the PCB from Rev A, I just decided to add just a couple of vias in for one of these byte lanes, and then route on the bottom layer, so top to bottom layer, so I don't leave any via stubs, going over to the memory module and up again through vias. And this is completely fine. We don't really need to take the via delay into account because this is, again, such a fairly low speed system. If you'd like to learn more about the PCB design aspects when it comes to DDR memory, make sure to check out video number 59 on my channel, which goes into FPGA and system-on-chip DDR PCB design tips. If you'd like to go into far more detail, I have a fairly recent course out called Advanced Digital Hardware Design, offered through Fedivel, which is 11.5 hours of content, which has a whole section on DDR3 memory and termination, as well as everything you'd like to know about FPGA-based hardware design, including gigabit Ethernet and so on. In the next video, I would then like to show you how I implemented this DDR2 memory as we saw from the Xerxes Revision B with a soft-core microblaze processor, how we can generate the structure and the HDL for this, generate a bit stream, and then program the microblaze to do some memory tests on our DDR2 memory to verify the functionality. This will be in a future video. I hope this video was useful to give you an introduction or some ideas of how you can generate your own DDR3 pinout and how you can interface an FPGA with some DDR memory. If you liked the video, please do leave a like, a comment if you have any questions, and make sure to subscribe to the channel to stay up to date with any new hardware, DSP, or embedded systems videos. Thanks again for watching, and I hope to see you in the next one. Bye bye.